Welcome back to the Nexperia Power Live Industrial Channel. We're already starting our fourth and final session of today.
And here live with us are Steve from Recom, our special guest, and Jan from Nexperia. Nexperia teamed up with Recom, a highly successful manufacturer of AC-DC power supplies and DC-DC converters. They will present a case study on how choosing the right power diode, our Trench Schottky rectifier, proved vital to the efficiency of the complete system. The session will last about 25 minutes. We will start with a presentation and then answer your questions. Questions are anonymous, and you can ask them by using the question pane on the right-hand side of your screen. Please ask your questions to the experts or share your own experience and insights. And with that, I will hand over to Steve and Jan to begin. Gentlemen, the floor is yours.
Thank you very much, Robbie and Petra. And hello and welcome to this webinar. So the development of power supplies can often be a very difficult process. They are expected to reach ever higher levels of efficiency while still being as compact as possible, of course. And cost is another important factor. And of course, it goes without saying that the power supplies must be reliable and safe. And Recom is a highly successful European manufacturer of AC-DC power supplies and DC-DC converters. For a recent project, Recom wanted to develop an AC-DC power supply which was intended for medical and other applications. And the goal was to create a solution which had double the power density of the previous model without sacrificing safety, reliability, or efficiency for that matter. So to get there, the development team had to use the latest advances in switching controllers, topologies, and components. And Nexperia was able to provide a system-critical component here. So my name is Jan Fischer. I'm a senior product manager at Nexperia, responsible for our power Schottky rectifier portfolio and based in Hamburg, Germany.
Hello, and my name is Steve Roberts. I'm from the Innovation Manager at Recom, responsible for new products and innovation ideas, based in Gmunden in Austria. So let me briefly introduce you to Recom. Our headquarters is in the heart of Europe, in the picturesque town of Gmunden, surrounded by the beautiful Austrian Alps. And in this inspiring location, we innovate and develop new ideas to make standard and customized power converters, as well as innovative platform architectures. So Recom products have proven success in all areas of electronics, from industrial automation through to transport, e-mobility, test and measurement, to medical and IoT. And the three main pillars of our success are innovative products, reliable customer support, and an extensive global distribution network.
Steve, can you tell us maybe a little bit about the products that you're offering?
Yes, Recom Power is a manufacturer of AC-DC electronic power supplies and DC-DC converters. We have over 30,000 different power supplies for use in a wide variety of applications with a best-in-class worldwide distribution service. But since we're talking about AC-DC power supply solutions today, let me elaborate a little bit on this specific category. And we understand, that today's AC-DC converters need to be safe, cost-effective, energy-efficient, reliable, and also significantly smaller than their predecessors. So we use the latest advances in switching controllers, topologies, and components to create these power supplies with, as you said in the introduction, with double the power density than previously possible, without sacrificing safety, reliability, efficiency, or thermal performance.
And maybe can you describe a typical challenge that you and the design engineers have to overcome during that process?
Yeah, so our team at Recom Power Solutions wanted to create a new kilowatt AC-DC power supply with multiple outputs, which we call the RACM1200-V. But before we go into the technical details, let's have a quick look at the product video for this part.
Innovation. Technology. Recom. We power your products.
Recom's new compact 1200-watt AC power supply unit with fanless baseplate cooling delivers up to 1,000 watts continuous and 1,200 watts boost power. The unique thermal management concept of the RACM1200-V permits cooling under all normal operating conditions, but enables the smart system cooling fans during heavy load and excessive temperature conditions. This gives you the best of both worlds: conduction-cooled operation and smart fan cooling at high ambient temperatures and peak loads. An integrated microcontroller monitors the input and controls the output voltage and alert signals for high operational reliability, making it fault-tolerant and maintenance-free. Modified firmware versions are available for customer-defined performance curves, which can be PM bus configurable. The RACM1200-V, the new cool. Recom, we power your products.
So as you can see from the name, the M in the product name indicates that this power supply is certified for use in medical devices. And the relevant standards, this is 6601-1 and 6601-1-2, are significantly stricter than the equivalent industrial standards. So we needed larger creepage and clearance distances, a better insulation grade, and of course we had to meet harsher EMC limits. And this meant designing the power supply is not so simple as with straightforward as an industrial version, which created unique challenges for both the design and for the selection of the components that we used. So another challenge was ensuring consistent performance under all operating conditions. So besides the main output, there were two auxiliary outputs. So a 12-volt 1-amp supply to power an optional smart cooling fan and an always-on 5-volt 1-amp output for control and monitoring purposes. And the design requirements were that the overall efficiency stayed high even when the main output was switched off, so that the standby power consumption was minimized. But again, it's not so easy to design a power supply that's efficient at both 1.2 kilowatts peak load and when delivering 5 watts or less in active standby.
I can imagine. So how did you solve the problem?
Well, the auxiliary 12-volt fan output is derived from the main output via a buck switching converter. But a separate AC-DC power supply was needed to be integrated for the always-on 5-volt output. It's basically an AC-DC inside the AC-DC. And the only available space for this additional circuitry was close to the high main output power components, which of course run hot when delivering the full output current. So we tried fitting planar Schottky rectifiers for both the DC-DC and the AC-DC auxiliary power converters, but they risk becoming overheated under full load and worst case conditions. So the solution was to use the new Trench Schottky diodes from Nexperia. The low forward voltage drops and the very low QRR were essential features to minimize the rectifier losses in each switching cycle of the two converters. In addition, the low reverse leakage current was very important for the DC-DC when the input-output voltage ratio is low, as the diode is longer in the off state due to the high duty cycle of the switching MOSFET. So frankly, without this one component, we would have had to change our power supply specifications for the worse.
That's interesting. So you were mentioning the low QRR of the Trench Schottky, and this is something we also see as one of the main advantages of Trench Schottkys over planar Schottkys. So I would quickly like to elaborate on the efficiency advantage that you can gain when using a Trench Schottky rectifier. So looking at the graph on the left-hand side, we see the reverse recovery behavior of a Trench Schottky versus that of a planar Schottky. And there are two main differences which I would like to highlight. So first of all, the QRR, which is the reverse recovery charge, which is essentially the area between the recovery curve and the zero line, is significantly smaller for the Trench Schottky diode. And this means that the associated switching losses in the diode are also significantly smaller. In this case, this is about a factor of 3 in this particular example. Second, what you see is that the maximum reverse current, so which we call here IRM, is significantly lower for the trench Schottky versus the planar Schottky. And the problem about IRM is that at the time when it is flowing, the diode has ideally already recovered and the MOSFET in the same commutation cell is switched on. So this means that the MOSFET has to conduct this current coming from the diode. And this, again, of course, causes losses in the MOSFET. And from the graph here, we see that the difference is about a factor of 2 in this parasitic current. And now what we see is the effect on the right-hand side. So this is the efficiency of a 48 to 12 volt buck converter that we have measured for different switching frequencies, and we compare the overall converter efficiency between a planar Schottky and a trench Schottky. And what you see is by simply replacing the planar Schottky by a trench Schottky, you can gain up to about 3 percentage points in efficiency, in this case for 500 kilohertz here. So this is a nice comparison, I think. And Steve, it's good to hear that you can also see similar benefits in your design. Were there any other factors that influenced your decision for a trench Schottky?
Yes, even high efficiency components will dissipate some power. So the ease of cooling the parts is also very critical to the design. As you can see, it's a very compact PCB here, lots of components in there. And the Nexperia Trench Schottky diodes use a copper clip bond technology to improve the thermal conduction out of the package into the board. So we were able to design our PCB with very low thermal impedance paths to dissipate the heat without needing to use any gap pads or additional heat sinks for the power diodes. And also the trench Schottky configuration improves the thermal stability of the diodes. So we could push our design to the limits without worrying about thermal runaway in the rectifiers. So this combination of factors meant that we were able to offer a power supply that can deliver 800 watts of main power and the full auxiliary power at 50 degrees C ambient without any forced air cooling whatsoever.
No, that's pretty impressive. So what I can say at Nexperia, we also have put a special attention to thermal stability and a large safe operating area of the trench Schottkys. And I would quickly like to explain the positive effect that the trench design has towards safe operating area. So in the left-hand graph, we see the simplified cross-section of a planar Schottky diode and a trench Schottky diode. And in case of the planar Schottky, under reverse bias conditions, we observe a crowding of electric potential towards the top of the device, which is basically seen in these lines here. And this means that in effect, the electric field, which is nothing else but the gradient of the electric potential, is very high at the surface of the device where the Schottky junction is located. And this results in an increased leakage current and high reverse power losses. In contrast, on this cross-section for the trench Schottky, you see that the bottom of the trench by construction is at the same electric potential than the top of the device. And this pushes down the electric potential into the depth of the silicon. And the effect is that the electric field at the junction, the Schottky junction, is reduced and the leakage current is lowered. And then, of course, the reverse power losses are reduced. And this effect is called resurf effect, reduced surface field, quite obvious here. And less power losses then directly translate into a higher thermal stability of the device under reverse bias conditions. And this is something we can see on the right-hand side here, because we compare the Nexperia Trench Schottky here to a competitor part. And in the graph, we see the maximum reverse voltage that is allowed to be put on the device as a function of the junction temperature. So this is a 100-volt Schottky, and it can be operated at 100-volt reverse bias up to a certain temperature. And then at this point, the reverse power losses in the device, they become so high that the thermal system, meaning PCB and package, essentially cannot dissipate this power anymore. And then we have to derate the diode. And what you see here, that the Nexperia part has a low leakage current and therefore an increased safe operating area. And this gives us in the design, in the end, an additional safety margin of about 40 volts in this case. But of course, not only the silicon design is relevant to avoid thermal runaway, but also the package of the diode and the PCB design play a crucial role here.
Yes, for us, we wanted to create a very compact, low-profile power supply that could fit inside a standard 19-inch rack mount enclosure. So this meant that the maximum height of the whole power supply had to be 40 millimeters or less. And a rectifier diode is not a particularly large component, but every little helps with such a high-density layout. And the fact that the Nexperia Trench Schottky rectifier is low profile and required nearly half the PCB space as the alternatives meant that we had much more freedom to place other components on the board to meet our size target.
Yeah, that is, of course, also one of the main advantages that we see of our modern clip-on packages. So looking at the left-hand graph, you see our CFP3 package is about half the size and half the height of the older SMA package. But still, as you see on the right-hand graph, the CFP package dissipates as much heat as the much bulkier SMA package. And therefore, it offers a very good chance for miniaturization of the design. So high power dissipation capability on a small footprint, that is a clear trend that we see and what also our customers ask us to deliver.
Yeah, sure. We've used Nexperia components in many of our designs, especially where we need high power dissipation. We can rely on the device and the guidance from Nexperia to choose the best component from our needs, from a simple SOT signal transistor, like the BC817K, which can handle 1 amp peak current, although it's so small, through to a trench configuration power diodes or to power MOSFETs. An example is in our next power supply project will be a 2 kilowatt design with ORing functionality. And the output MOSFETs have to withstand both high continuous and very, very high peak fault current conditions. And we found that Nexperia is the only manufacturer that offers a suitable MOSFET that will fulfill these very demanding requirements.
I'm, of course, very happy to hear that. Thanks a lot for sharing your experience and expertise with us today, Steve. Also, in my view, the collaboration with Recom was excellent, and also your technological achievements in this power supply are very impressive.
Thank you.
And okay, I propose that now we open the stage for questions. So the attendees, please share your questions and insights and enter the discussion with us. Thank you.
All right. Thank you very much, gentlemen. Very informative session. Great to see this collaboration and partnership. We actually do have a couple of questions already that came in. I'll start with a question, I think, for Steve. On how many layers of PCB is your design made?
We use basically an 8-layer board. There's a kind of comparison between the cost of the board and the complexity, but 8 layers is kind of like the sweet spot for us. It's either 4 or 8.
Okay. Thank you. Then the next question, what is the maximum current of the power supply per power rail?
Well, the limit is 1200 watts. So, and we have 24 volt, 36 volt, and a 48 volt output. So you can basically do the calculations for the maximum current. The nice thing is that we can adjust the current limits. So if you want to set the current limits yourself, you can set that using the PM bus interface. Or if you want for us to preset the current limits for you, or to set some sort of overcurrent curve, so it'll accept so much overcurrent and then go into current limit. We can do all of that. It's got a digital control loop inside, so it's a very flexible power supply.
Perfect, thank you. Question for you, Jan. You have shown the comparison of safe operating area between a Nexperia Trench Schottky and a competitor part. Is this competitor part a Trench Schottky as well? And if yes, why is the Nexperia part thermally more stable?
Yeah, the competitor part is also a Trench Schottky, so in that case it's an apple-to-apple comparison. And the difference in thermal stability and safe operating area essentially comes from a difference in the Schottky barrier height. So when you design a Schottky diode, then you have a choice for the metal that you want to incorporate to have your metal to semiconductor interface. And this metal determines the barrier height. And at Nexperia, we have a relatively high Schottky barrier that we chose in order to reduce leakage currents and to enable larger safe operating area.
Okay, thank you very much for that answer, Jan. Then back to you, Steve, one more question. Is the RACM1200-V series available with a digital interface?
Yes, as I mentioned, the main control loop is a digital control loop inside there. So we have a version with an external PM bus interface if you want to adjust this or access yourself. This allows the user to set the output power, the voltage and current limits, to monitor the internal temperatures, and to get alarm and status signals. And also to modify the control loop characteristics. So, for example, as I said before, you can choose whether the power supply delivers constant voltage or constant current, or you can change the ramp-up time or the transient response. All of these are available under the PM bus version.
Okay, great. I think we still have time for one more question here. What are the special requirements for medical-grade power supplies? Do they need to be especially reliable, for example?
If I can answer that one, the safety certifications focus is, of course, on safety, patient safety. So medical grade power supplies have to have 2 MOPP, that's means of patient protection, so that they're double fault tolerant. And they have to withstand higher transients and surges and have isolated output so that the reverse currents cannot harm patient safety. So, for example, the RACM the 1200-V has a filter requirements for body floating. So that means the patient leakage is less than 100 microamps. So it's a much more complicated design. And the last thing is the EMC. It wouldn't help, for example, if you had 2 pieces of medical equipment placed next to each other and they interfered with each other. So the EMC requirements for immunity are much more strict than with industrial equipment.
Okay, thank you very much. I think we still have a question coming in here. The audience loves this topic. Would the supply practically deliver 1,000 watts without thermal over temperature?
Yes, it would. It's basically it's basically cooled, so it depends on how big your heat sink is on the base plate. So if you are able, for example, to water cool the base plate, then you can deliver continuously 1,000 watts, no problem.
Can I take one more question? All right. The power supply you have discussed is an industrial grade power supply. What about automotive DC-DC converters? Are the Nexperia parts also RACM1200-V qualified?
Maybe I can take that one. Yeah. So yes, in general, our parts are all RACM1200-V qualified. So for many parts, we have different part numbers available now. So you have versions that have a -Q as a suffix, for instance. These show you that it's an automotive grade diode. So yeah, for our latest and these trench Schottky rectifiers are already participating in this split. So our latest products we have split into an automotive grade version and a non-automotive version. So you can get both, but essentially all our components can be purchased as an RACM1200-V compliant part. Yes.
Good. So I guess that brings us to the end of the live session today. So thank you, Jan. Thank you, Steve. Thank you, Recom.
Thank you.
Great session, great collaboration. And if you want to know more about power diodes or about Recom power supply, you can, of course, follow the resource link underneath the screen or chat to one of our power experts in the live chat box. And the full case study is also available for download from the portal.
This concludes our industrial channel and the first day of the Power Live event. We hope to welcome you again tomorrow when we will share with you lots of insights about in the automotive channel. So, thanks for watching and have a great rest of your day.